They're here. It's logarithm day. Woo! So, here we are. Yes, indeed. It's time for everybody's favorite logarithms. So, let's find out what's a logarithm. Well, of course, in order to get you to understand a logarithm, I have to first go back to our exponential functions. What were exponential functions? They were functions which had a constant base and a variable exponent. And if you'll recall, we put some stipulations on them. We said the base had to be greater than 0, couldn't be 1. We said that y would also then, because the base is greater than 0, y is always going to come out greater than 0. X could, of course, be any real number, which then, more specifically, if you translate that, said that our domain for exponential functions was any number from negative infinity to positive infinity, but our range for y-coordinates had to be greater than 0, going to infinity. Okay, because that very concept is what's going to lead us to logarithms. Okay, that was actually called exponential form. Let me label that, and this is going to be logarithmic form. And I'll come back and fill in the specific details in a moment. But if you recall, somebody in the deep dark past decided, hey, we needed a logarithm. And actually that somebody was a man by the name of John Napier, who developed them in 1614. But you have to understand, Napier wasn't doing logarithms for what we're about to use them for. Napier was just trying to make his calculations. He was a scientist and astronomer, trying to calculate distances between planets and stars, working with these gigantic numbers, and the calculations were just nothing short of horrible to do. And so he was trying to find a more efficient way, and he found a way that if you converted numbers to scientific notation and turned them into logarithms, suddenly horrible numbers you needed to multiply could just be added. Hang on to that thought until next class when we talk about the properties of logs. But where logarithms actually come from is the basic old concept. They are the inverses of exponential functions. Now, how did we create an inverse? Well, we switched our x and y. And then the tricky part, we were supposed to solve for y. And this is where there was issues. How do you solve for y? It's an exponent. So in mathematics, of course, when you can't do something, you create new notation, invent a new theory, and of course, prove it to be true. That's the key factor. And so establish that if you want to solve for an exponent, that we're going to, if you want to solve in this case for y, we're going to call it a log. And then, of course, you had to keep track of the base number, so they said we're going to make that the subscript on the log. So it's read log base b. You had to know what you were equal to, so log base b of x is how that's read. Now, let me go back up here and write it specifically, transferring our exponential form to our logarithmic form. If you take this one written y equals b to the x, a logarithm would solve for which one of those three variables? And of course, you're saying it would solve for x, because it's the exponent. So I would have a log with a base b of y. That's how you interchange between the two forms. And we are going to practice that fairly substantially here in a few moments. I want to point out then that the restrictions we put over there on exponential functions carry over to logarithms. Our base still has to be greater than 0, can't be 1. So you can have fractions between 0 and 1, just can't have 1. Now, since over there, x could be any real number, over here, x can be any real number, and y has to maintain a number greater than 0. But is that still maintaining the same domain and range? Because now we reverse the variables. So now, in this case, our domain is our y here. Y is in the position of normally where x is. So now it's switched. So now our domain is going to be from 0 to infinity. And our range is going to be negative infinity to positive infinity. Because what a logarithm can equal, the y, what's over here on the equal sign, that's going to be the range. So it kind of makes sense, though. If these are inverses and we just switched x and y, all I did is I interchanged the domains and the ranges. And that's exactly what should happen when you do an inverse. They should interchange. Okay, for you all, the key factor is the domain must be 0 or greater. The base must be greater than 0. So the easy way to remember it, any number which is part of the log must be positive. So in this case, that would be b and y. Anything attached to the log has to be a positive value. That's the easiest way to remember it. And I'll be beating that into you for several days here. Okay, there you're going to have a few problems that are going to ask you for the domain of a particular problem. So once again, remembering logs, I'll write it in normal form now. Logs, their domains must be positive numbers, 0 or bigger, which is our main concern here. So if I give you a log, say base 7 of x minus 3, and they're just going to flat ask you what would the domain be, okay? If they want you to find the domain, they want to know what values of x you can put in there will keep it positive. Well, dudes, how do we figure out where things are positive? How have we found out where everything is going to be positive or negative? Yes, always and forever, it's our favorite activity. We test points. And we test points, and we test points, and we test points. Let's face it. Testing points, if you want to know where positives and negatives are, it is the way. So, in this case, all you're worried about is what's going to keep x minus 3 positive. What's going to keep the inside of that log positive. So you're going to go, okay, well, what makes that quantity there equal 0? Well, 3 looks like the key number. Okay, test a point. 0 would be to the left. That's going to be negative. So the other side is going to be positive. I want the positive values. So therefore, I want all the values on this side. Now, can I include 3 or not? Can I have the number that makes it equal 0? And the answer is no, you can't have the log of 0. So this one's just going to be parentheses 3 to infinity. And you've found your domain. Finding domain is not that tricky on a logarithm. Let's do one more here. Suppose I gave you log base 6 of the quantity 4 minus x squared. Notice the base has absolutely nothing to do with the domain. So you would go, okay, I'm just trying to keep positive values in there. How do I do that? Well, I'd have to test points. What numbers make this thing equal 0? Well, you got two choices. You can either factor it or you can solve it. In this case, I'd probably just solve it. And when I square root both sides, I will get plus or minus 2. Note that also would have factored as 2 minus x and 2 plus x, whichever way floats your boat. But I'm going to have those two numbers on my number line. Okay, if I test 0, which would be in the middle, 4 minus 0 is positive. You'll recall all these squared ones, we would end up with one thing in the middle and the opposite sign on the outsides. So which one do I want? The positives or the negatives? Well, with logarithms, you always want the positives. However, you cannot ever have the endpoints. You cannot equal 0. It'll always be parentheses. So in this case, the domain is -2 to +2. So finding domain is not that involved. Okay, before we get to solving equations, let's take a look at the graphs of logarithms. So we're going to go create a graph page here, and I should have done that in advance, sorry. But okay, how do logarithmic graphs relate to the graphs of exponential functions? Well, pretty basic. We're going back to our basic exponential function from last class. And we would have 0, 1, 2, 3. And you learned, of course, not 0. That would be 2 to the 0, 2 to the first, 2 to the second, 2 to the third. That gave us 1, 2, 4, and 8. Okay, I'm going to go ahead and put that one on the graph with a horizontal asymptote and points plotted at 0, 1, 2, 4, and 8. Okay, we know our basic exponential function. How do you suppose we would ever possibly get its counterpart, the log base 2? Of course, it has to have the same base. Well, given that we just said they were inverses, and what do inverses do to the x and y coordinates? Inverses simply reverse them. So I'm putting the 0, 1, 2, 3 on the left. Guess what goes on the right? Yes, our 2 to the 0, 2 to the first, 2 to the second, etc. Or our 1, 2, 4, 8. So now plot those as those coordinates read. That's 1 over and 0 up, 2 over 1 up, 4 over 2 up, 5, 6, 7, 8 over and 3 up. So clearly I have a curve going off to the right, but it can't just dead stop there. The other exponential function followed an asymptote. Where do you suppose this one goes? And hopefully somebody out there is yelling, well, of course, it's got a vertical asymptote, and it does indeed have a vertical asymptote going smack down the y-axis. And so, yes, logarithms go down the y-axis. Now remember, we just said their domain was greater than 0. Look at this graph. It only exists for x coordinates on the right-hand side. It only has x coordinates greater than 0. Where exponential functions grow exceedingly fast, logarithmic functions grow exceedingly slow. They are just so slow you can hardly stand it. Because think about it. We're only up 3 units and we're 8 over. 16 units over to get up 4. 32 units over to only be up 5 squares. That's a lot of over and not much up at a time. Okay. The good news is, other than that, logarithms function pretty much just like your exponential functions. So this shouldn't be a gigantic shift for you. Other than oops, sorry, I don't want that one. They're a little bit interesting to flip. So we're going to do a little bit of negative action here at the same time. I want to graph this logarithm, which is a negative log base 3 of x plus 4 plus 2. Okay, shifting rules are identical to what we've done now for some of you 3 years. We're going up 2, we're going left 4. You, of course, want to do that first. Up 2, left 4. That's your new origin. What kind of an asymptote should you run? Logarithms, always think of exponential functions have an x in them, so they have an x-axis asymptote. Logarithms, look at that L on log. It's a straight up and down line, so its asymptote is straight up and down. Okay, you need a t-table to graph this one. Since it is a base 3 log, we are going to plot points like 3 to the x. Which side do I put the 0, 1, 2, 3 on? I have reversed it, so I'm doing the right side, which means the left side is my 3 to the 0, 3 to the first, 3 to the second, 3 to the third, or 1, 3, 9, and the 27 we're not going to plot. Okay, so we know we have these coordinates. Now, I was being extra evil here, and I threw a negative on the front. What kind of a flip is the negative out front? That is an x-axis flip. That's upside down. Now, for some reason, logarithms people are driven crazy by how to flip logarithms. So I'm going to highly suggest that you come over and you draw yourself a normal logarithm. Remember, normal came up the axis and curved off to the right. Okay. An x-axis flip, in my opinion, is the hardest one to draw. It makes your brain think. I'm flipping this thing over the x-axis. So this piece that was going down the asymptote will now be going up the asymptote. The part that was curving above the x-axis will not be curving below the x-axis. So it's going to look like the red line I just drew. I'm going to plot it using these points we have here. So from my origin, I'm going 1 over 0 up. And then I'm going, it says go 3 over 1 up, but in this case, I'm going 1 down. It's negative. And then I'm going 9 over 4, 5, 6, 7, 8, 9, 2 down. I'm not going to have room to get the 27 over. And you can see I'm curving underneath, and so I'm just going to curve outward here, and then I know I have to go up the asymptote. There is something about logarithms that just plays with people's brains. Now, before we can do our last graph, I should have done this earlier. I have to ask you, we're going to graph something with E in it, but I have to ask you if you remember the 2 special kinds of logs that are used more than any others. We learned back in Algebra 2 there were common logs and there were natural logs. They each have their own special base. Common logs were logs with what base? Someone out there saying base 10, because yes, base 10, given that our number system is base 10, we write scientific notation with base 10. We were using base 10 a lot, so they said not going to write the little 10, just going to write log. So anytime you see log and there's no base 10 on it, no base there, it is a 10 automatically. The other one, yeah, well, if it's got to do with nature, then it's got to deal with our good friend E. Natural logarithms are logs base E. Once again, they wanted special notation to write quicker, more efficiently. They went, boom, that's a natural log. So we write ln, logarithm natural log of x. Okay, everybody knows that if it's a natural log, that means it's actually a hidden little base E log. Natural logs are base E logs. So I want to graph a natural logarithm just to make sure you're up to speed with how to do that. So let us get one ready here. We won't draw anything super-duper fancy, but we'll put a little zip to it. Suppose I said, let's graph a natural log, and of course, you all want some pizzazz in your lives. So let's do a natural log of 5 minus x. I won't even put a vertical shift on it. But what evil thing did I do? Well, A, it's a natural log, which means it's base what? It's base E. Okay, but the other thing I did is, can you tell me which way it's shifting? No, you can't, because you're not allowed to have a negative on the x, so we'll do like always. We'll factor the negative out, make it x minus 5, which therefore means I'm shifting this thing right 5. So let's get that done first. We have right 5. What kind of an asymptote should I draw? Logarithms. Look at that L. It comes straight down. We go straight down with our asymptote. Okay. Now, I need a t-table of values to plot. With logarithms, the 0, 1, 2 goes on the right. What base am I using to get my points on the left? I'm using base E. So if you practiced on your last assignment, you know I have to know the powers of E, at least the first two. E to the 0, of course, is 1. The first is 2.7, and the second was 7.4. So those are the numbers we're going to use to plot it. Okay, what kind of a flip do I have because of the negative in front of the x? The negative was on the x. That's a y-axis flip. So let's think about that in terms of our graph. If our normal logarithm comes up the y-axis and curves right, what's this baby going to do if it flips over the y-axis? It's going to come up the y-axis and curve left. So I think that's a much easier flip to do when it's flipped over the y-axis. Much nicer. So when it says plot 1, 0, we're going 1 left. Then we're going over 2.7 left, up 1, over 4, 5, 6, 7.4, up 2, and I'm off that away. Curved off to the left. There you have it. Your natural logarithm. Okay, that's graphing. I'm going to break the video right there for the moment, and then we'll come back and start solving some problems with log.